I hope this is not an overdose of theory for you. I try to build it up slowly as well. This is one of my favorite subjects, as if there's anything I talk about that's not a favorite. Trouble is too many favorite subjects. But uh, the question as to why the universe is magnetized seems to me as exciting as the question of why did the universe begin a finite time ago. I remember when I first came as a graduate student um, to Princeton, um, there was a book by Hawking and Ellis, The Large-Scale Structure of Space-Time. It's quite prevalent at the time. And if you open the book and you read the preface, it says that in physics we have learned that the universe began a finite time ago. You know, it shook me to the core to read a sentence like that written with such clarity because you grow up where you grow up, and many people tell you that the universe has always been around from minus infinity to plus infinity. Well, physics certainly has shown that that is not quite the case, that it began a finite time ago. So it's quite exciting that there are some questions we can settle with such certitude. Why is the universe magnetized is a very general question because magnetic fields are ubiquitous. The mechanisms are not the same everywhere, but there is a persistent tendency for the universe to generate magnetic fields even when there are none. And dynamo theory is that very large and exciting body of knowledge, which has been an open question now. It's not quite as old as the problem of turbulence, but is a problem that um, involves turbulence in such a deep way that it's hard to separate the two. It just is that it's more the properties of turbulence that determine whether you can start out with a chaotic universe and end up with large-scale magnetic fields. And I'll get to that in a moment. Before I proceed, I would like to acknowledge Matthias Rempel, my partner in crime. We teach a summer school often in Boulder every year, and I borrowed heavily, and he has borrowed from mine, so we go back and forth sharing notes all the time. And he works on the solar dynamo problem and has done some of the most beautiful work on sunspots, which it's a very complex and beautiful phenomenon, but takes very high level of numerical simulation to get it right. So a few beginning comments. I began by saying, why is the universe magnetized? And I'd like to address a few questions. And you'll see that the magnetic fields, as it is present in various situations, has different forms, lifetimes, and so on and so forth. In the Earth, the magnetic field has been present for a very, very long time, 3.5 times 10 to the power 9 years, much longer than the ohmic decay time, 10,000 years. It has strong variability on shorter timescales of 1,000 years. The Earth's dynamo problem has been addressed by large-scale simulations. It has a molten core, which people feel is at the heart of magnetic field generation. As to whether these simulations truly describe or are well resolved enough to have nailed the problem definitively or not is a matter of who you talk to. At a certain level, people feel that they understand within the realm of numerical simulations possible today that they understand it, but people who are fastidious question it. Planets such as Mercury, Jupiter, Saturn, Uranus, Neptune have large-scale fields. You will see this emphasis on the large scale occurring repeatedly in my talk. A little later, I will make a distinction between what I call the large-scale dynamo and the small-scale dynamo. And it's my sense that the small-scale dynamo problem is largely a solved problem. But that does not explain the large-scale dynamo, which is really the most persistent and unsolved problem as yet in plasma astrophysics. Getting on, planets have their own large-scale fields. The sun, as much as we can see, and there's a lot that we can see, magnetic fields from the smallest observable scales to the size of sun. This magnetic field has a striking feature, a beautiful striking feature, the 11-year cycle of the large-scale field, which reverses sign every 11 years. And I'll show you data that demonstrates that conclusively. The ohmic decay time is 10 to the power 9 years in the absence of turbulence. Why am I making a point of mentioning the ohmic decay time? It's a little bit of this argument that we were going through with the reconnection problem. If you know the resistivity and if you have a magnetic field, then the magnetic field will decay. No question about it. What will it decay on? The time scale of resistive diffusion. So if the magnetic field on Earth is living a lot beyond 10,000 years, you have to figure out what the mechanism is. So is it for some of the others. Other stars, and what is very interesting is my dear friend Stephen Bulbus once told me that when he was a graduate student, it was not respectable for astrophysicists to learn about the sun. And they all lived in different communities. I mean, Parker was a very atypical example. He straddled both. But the astrophysicists didn't really talk to the solar physicists. They went to different meetings. And to some extent, this remains true, except what we know about heliosseismology or the solar convection zone has changed this somewhat, because people have come to realize that below the sun's surface, they now know, thanks to heliosseismology, a few things that could be of great applicability to stars, at least stars which are similar, because the sun is a typical star. So other stars have convection zones which are very similar to sun. Stars with outer radiation zones, most likely primordial fields. What people are talking about here is this whole competition between the time scale of decay of a magnetic field and the need for invoking dynamo. This question is not always clear-cut. It is clear for Earth, it is clear for certain areas of the sun, but it is just possible that in some cases you don't need dynamos to understand why the magnetic field is hanging around. It might just be that they might have been primordial, present due to conditions at the time of birth that simply haven't decayed away. And so I'm not going to say that every time you see a magnetic field in the universe, you should jump to astrophysical dynamo theory. You should go and necessarily look at what the timescales are for resistive diffusion, separating this out. Is the magnetic field lived a lot longer than resistive diffusion allows, and make your conclusions based on it? Galaxies are in the kind of situation, if you look at Russell Culster's discussion of the galactic dynamo, he'll tell you that since dynamo theory, large-scale magnetic field generation is not a solved problem. You sometimes wonder whether you can solve the problem without invoking dynamo theory. Galactic magnetic fields are at that sort of crossroads, where the timescale of resistive diffusion and the life of the magnetic field are kind of comparable, so you're wondering whether you can get away with a primordial magnetic field assumption. I present this large range of possibilities to you to simply make the case that at the end of the day, there are very many astrophysical objects, including some in the heliosphere, including the sun, where the persistence of the magnetic field or its reversals are not well understood from first principles. And we therefore need to study this problem. And people have tried, therefore, to solve this problem. And the first thing that they have tried to do is to try to understand from MHD equations whether they can understand how large-scale magnetic fields can evolve given a certain background that you start with. So let me make a qualitative statement here, and then I will go and return later on and make the large-scale dynamo problem mathematically more precise. These equations you know. You've seen them throughout this summer school. And I write them out. Matthias Rempel has these equations. He's much more of a numericist than I am, and he studies sunspots using these examples. So that's your continuity equation, the first one. Pascal derived it for you for a hydrodynamic case. The MHD case doesn't change. It remains the same. She also mentioned to you, as Blakesley must have as well, that the Navier-Stokes type of equation gets modified due to the presence of magnetic fields. And in red are indicated the magnetic field terms, the Lorentz-Force terms, the viscous terms tau. I'm going to return to that next slide. You can write an equation for the internal energy, which obeys an equation like that. The fourth term there is your heat conduction term, and there's dissipation due to viscosity and resistivity. And you have the Ohm's law that you've seen me already talk about in the context of reconnection. By the way, reconnection is going to rear its head sooner or later, and I'll talk about where it becomes important. So the assumptions clearly are that the continuum approximation is good. And in the very beginning, we'll start for non-relativistic motions and low frequencies. If you go to the realm of relativistic situations or where general relativistic effects are very important, these MHD equations get replaced by GR MHD equations. They too have dynamo issues. Lots of exciting work going on there right now for compact objects, accretion disks. Charles Gammy talked to you about accretion disks a little earlier in this summer school as well. This problem of why they're magnetized is a problem that we're all spending a lot of time thinking about. I want to finish discussing the equations. The viscous stress tensor tau can be written in this form, and these are directly from Landau-Lifshitz, if you will. Don't forget about the indices. Just be satisfied that people have derived a closed set of equations, that they're indicating the dissipation term, eta j squared. The equation of state is written, P and E are related by this quantity. So eta, nu, and kappa are viscosity, magnetic diffusivity, and thermal conductivity. Mu 0 denotes the permeability of vacuum. You have a complete set of nonlinear equations. We're not going to worry about every term in these equations, but you really want to focus on the fact that you have an MHD model and you're trying to understand how large-scale magnetic field grows. Let me first start with the induction equation. Ampere's law, curl B equals mu J, yields for the electric field this equation, E equals V minus V cross P plus 1 over mu 0 sigma. Sigma is the conductivity. You could write it as the eta. And this is the induction equation that we just wrote. You've seen me write this before in the previous lecture. Eta is related to sigma to this equation. Let's focus on this equation. Let me ask you a question first. Suppose if you look at that equation by itself in B, what kind of an equation is it? It's a partial differential equation. But what is it? Linear, nonlinear? It's nonlinear. Okay. Tell me why you say that, and then. Linear in B. And you make a. So V cross B is in fact a potentially nonlinear term if you take into account the full extent of the MHD equations, because you know V obeys something else. But if I told you that V is given, that's an equation in B. Mathematicians love linear equations because they know how to solve them in many cases exactly. So the first problem that they tried to solve was this. If I give you a velocity field, can you show how B fields amplify? Came to be known as the kinematic dynamo problem. And the idea was that surely nature is creative enough to generate all kinds of velocity field. So surely a good bet is just assume that you can control V and figure out under what conditions you can have B grow. Linear problems have exponentially growing solutions. The question then becomes, can you under certain conditions of V find conditions under which B will grow? This is a kinematic dynamo problem, and if you go back and look at the literature, it's a very rich literature full of mathematical theorems and stuff like that. And all of those are true given the kinematic dynamo problem. But most of it is inapplicable. We now know better because we have solved the full extent of MHD equations, and we find that very few of the lessons of kinematic dynamo theory really persist in the nonlinear regime. Sad but true. So the nonlinearities of MHD catch up with us, but I'll get to that later on. Let me first leave with this equation And let me introduce some dimensionless parameters. Just like we did in the previous lecture, let's introduce a typical length scale L, a typical velocity scale U, and L over U is time unit. Using these, let's non-dimensionalize this equation. This is not surprising to you. This is something that we have done. You had me do, instead of RM, introduce S. Remember? And I told you that sometimes S and RM confuse people because S is usually done with the system size, but RM, the length script L, can be made to vary. So this is written a little bit more generally in terms of this L. Rm less than 1 is diffusion dominated. This just has decaying of the magnetic field. And you get a tau diffusion that goes like L square over eta. Left a magnetic field to itself, that's like leaving a magnetic field in a conductor. It will diffuse and it will decay. And just like temperature distributes, magnetic fields decay. And we won't get a whole lot out of that. But if we actually put in the velocity term, and the dissipation is there in addition, we have three types of terms. The advection term, this is shear. It gives you you can sort of see, it depends on B dot grad V. If the background flow is very sheared, you could see maybe there is a way for B to grow. And this is in fact amplification through compression. You start out with a magnetic field and you squeeze it lower, flux compression or flux, B dot dA constant might lead to amplification of the magnetic field. So all of these terms have to take into account when you take into account the effect of convection in the problem. So to summarize at this level, for V equals 0, the magnetic field decays on time scales of tau d equals L square over eta. You're with me on this, right? Agreed? Right? In Earth and other planets, evidence for magnetic field on Earth is about this. Well, tau d is 10 to the power 4 years. Permanent rock magnetism not possible since T is over T Curie and field highly variable. So field must be maintained by active process. And the way in which dynamo people think about it is the Earth has a molten core. Okay. Going back to Sun, the evidence for solar magnetic field is for 300,000 years. Most solar-like stars show magnetic activity independent of age. Indirect evidence for stellar magnetic fields over lifetime of stars, but tau d is 10 to the power 9 years. So here is where the question is less than clear cut. If tau d is this long, and I'm looking at magnetic fields of the order of this years, you would say, come on, you haven't come to a diffusion time. How do you know that magnetic fields by themselves have not simply persisted primordially? And why are you going off the deep end talking about dynamo theory? Well, people strongly feel that if the primordial field could have survived in the radiative interior of the sun, if you look at the sun, out from the core to about, say, 0.7 RS, if you have a lot of radiative dominance going on in the sun's core, then you hit what is called by helioseismology the so-called tachocline, where things change abruptly. Then you go to the convection zone. So their point is that if you had a magnetic field in the radiative interior of the sun, and everybody knows the sun has a field outside, so imagine that there's a magnetic field that rises to the convection zone and gets out to the surface, and it's what we see. But the convection zone has a much shorter diffusion time scale because the intuition is it's a very turbulent system. So even if you had magnetic fields that rose from the interior, hit the tachocline, but then they would be immersed in this turbulent bath, and the diffusion time there is really much shorter than your 10 to the power 9 years. And therefore, people feel that if we see large-scale magnetic fields that have survived the turbulence in the convection zone, it's because there must be a dynamo mechanism. So this sort of a discussion goes on and motivates our things. It's sort of good to keep these things in mind. The typical length scales, the velocities, the magnetic Reynolds numbers, and so on and so forth. And one of the things I'd like to point out to you is that if you look at the sun with the plasma conductivity, if you didn't invoke any turbulence, then in fact, you could say that the sun's diffusion time is really much, much longer and you don't need a dynamo. But people feel, looking at many other things at the same time, that really the effective magnetic Reynolds number is a lot smaller in the sun, and that the diffusion time is more of the order of 3 years. These are all based, I don't mean to suggest that there's a rigorous theory for all of this. This is just based on a lot of helioseismological measurements of things, how rapidly magnetic fields move from a distance of 0.3 RS to above, and trying to use computer codes to make sense of it, quite apart from the issue of magnetism. And they actually come up with estimates that are much less. Liquid sodium lab experiments, one massive one set up in Germany. There is another one in Madison, Wisconsin that Kerry Forrest has set up. They try to do an MHD system where they would actually have similar RM, but there has been no laboratory experiment successful to this day that have conclusively measured the dynamo coefficients that I'm going to talk about with a great deal of precision. Things people try, but these are very, very hard measurements. And so in Madison itself, we have 2 experiments, a liquid sodium and a plasma experiment, and we all await results. Hantao-G has an MRI experiment at Princeton, which tries to solve the MRI dynamo problem. And one of the difficulties that he has had over the years is, first of all, to really set up the magnetorotational instability uninhibited by boundary conditions, which are always a complexity in lab experiments, and then to actually be able to measure the fluctuation amplitudes, which tend to be very, very small and require extremely sensitive diagnostics. So part of the ways to succeed in this laboratory experiments is to build new diagnostics which can pick up low turbulent amplitudes. The process goes on. We all look forward to new results, but it has been slow coming. With that background, I'm going to proceed on the assumption that the fact that we have so much magnetic fields in the universe calls for an explanation, which at a qualitative level, we would like to get at some robust answers. So the kinematic dynamo problem that was set up in the very beginning, and notice what people have done. They have eliminated all the complexity of MHD, and what they're saying is, let's divide the problem in 2 parts. One is the complexity of MHD. The other is to say all that complexity does is to give you a velocity field. And now you ask yourself, can that velocity field amplify your magnetic fields? Okay, so you write down the induction equation. Outside you have a vacuum field. It's a jump condition across the surface. Del dot B is 0. V is 0 outside S. N dot V equal to 0 on the surface. E kinetic is half rho v squared dV is less than E max. V is a dynamo if an initial condition B equals B0 exists, so that E magnetic ends up being larger than E min. In other words, you gave it a certain velocity field, okay? So the kinetic energy is bounded from above by the velocity you started out with. If you start out with a B equal to B0 and you generated enough magnetic field energy that is larger than the minimum kinetic energy you have, then you could say that the velocity was responsible for the amplification of the magnetic field, okay? So this is dynamo. It doesn't make any distinctions between small or large, but now suppose if I break up the mean magnetic field, the total magnetic field into a mean field and a fluctuating part, so write your B as mean B plus fluctuation, then E magnetic will have one part that is the mean magnetic field square, a cross term, BB bar, right? That's going to average out because it depends linearly on the fluctuating amplitude. It's going to average to 0. Are you with me? Right? That's the definition of the fluctuation. And then you get a mean square contribution from the fluctuation energy. The small scale dynamo, now I'm separating out the following. The small scale dynamo is one in which the mean magnetic field energy square is much less than B prime square. So it's dominated by fluctuation energy, not by the energy of the mean magnetic field. On the other hand, the large-scale dynamo has the opposite property, that the mean magnetic field square is greater than or equal to B prime squared. So almost all turbulent chaotic velocity fields are small-scale dynamos for sufficiently large Rm. Let me stop and explain what that means. Suppose you have a turbulent bath of fluctuations. You often find that in these turbulent systems, the system fluctuations adjust so that they get to some sort of an equipartition between the magnetic and the field energy. But it's energy we are talking about, not flux. How does energy go? Energy goes like B primes squared. So if you could have a fluctuating field, which is very rapidly varying in space and time, which has energy in it, but doesn't have any flux in it. That is your small-scale dynamo. You can't say that starting out with turbulent velocity field fluctuations, you generated a certain amount of mean magnetic energy. But that mean magnetic energy does not organize itself into large-scale structure with finite flux in it. If you look at the Earth's magnetic field, and if it is a dynamo, there is a structure to the magnetic field. This large-scale structure goes from magnetic north to magnetic south. Of course, there's fluctuation around it, but you average out the fluctuations over a small space scale or a small time scale, you will be left with a remnant magnetic field which has large-scale structure. That is what I call a large-scale dynamo. Now, I made the comment that turbulence comes into dynamo theory in an inextricable way. There are plenty of dynamo simulations and theories which show that if you start out with fluctuations, you can, even if the magnetic field were initially weak, you can generate magnetic field fluctuation energies till they rise to equipartition. In that sense, the calculation of the saturated spectrum of those things, how it depends, what sort of a structure it has and how it decays, standard MHD turbulence theory knowledge applies, and to the extent we understand Goldreich-Sridhar spectrum or Kolmogorov spectrum or Urashnikov-Kraichnin spectra, they are all spectra for which you can get heuristic arguments. We can say we sort of understand how that comes about. Though that's really not first principles, we still have a sense of how that comes about. All of those things are therefore regarded as relatively well understood. And there's a very nice review paper by Alexander Shekochihin which summarizes the status of small-scale dynamo theory. You can look at that and he more or less tells you where things are there. The large-scale problem is in a very different place. And that's the one that is the focus of today's lecture. And what you will see is that large-scale dynamos require additional large-scale symmetries. And even when you impose these symmetries and you come to conditions when large-scale magnetic fields grow, you will find that there are some major obstacles to that theory being in a satisfactory state. And I'll talk about that. Well, what does it mean to have large and small in practice? Well, the heliophysical system, unlike many others, there's a lot of data. The sun has been analyzed and... Go ahead.
Oh, sorry.
You raised your...
I have a question about this decomposition. So it's a question of where the magnetic energy is not kind of the origin of the dynamo, whether it kind of began in small scales or somehow some instability caused something at large scales. It's just where it is.
Well, there are two issues. One is that suppose if you have a small scale, suppose you're given a velocity field. As I was saying, imagine I gave you that choice. So really MHD will determine to some extent, even if you started with a velocity, you knew how would magnetic fields work back on it and change it. But let me postpone that discussion for the moment and say, you give me a velocity field, and the question is that if you had a very small scale magnetic field like a seed, could the given velocity field amplify that? And in the context of astrophysics, there was a source of this called the Biermann battery. It turns out that if you go to the generalized Ohm's law that I talked about in my reconnection lecture, there is this term grad P over N. If you take the curl of that, then you get grad P cross grad N, which is called the Biermann term. And you can show, that's what is called the Biermann battery term in MHD. You can show that it can spontaneously generate very, very low level magnetic fields for you. But to amplify them, you can use your velocity field to amplify them. But you can do the amplification in two ways. One is that the scales remain small, but the energy is increasing. And the other is building up of a large-scale coherent structure that even though there are aspects of the magnetic field that are very disordered, out of turbulence, which is nearly chaotic, emerges a large-scale structure. There is no theorem in MHD that says that that sort of a inverse cascade from small to large scales will occur. Why do I call it an inverse cascade? Because typically in turbulent spectra, you stir at the large scale, the energy goes down to smaller and smaller scales before it is dissipated in a manner in which we indicated, right? In this case, though, you're starting out with a highly entropic state, highly disordered state, and somehow large-scale structure emerges from it. There's no theorem in MHD that says this must happen in 3D. Therefore, the large-scale dynamo problem has an additional burden on it. You have to show not only how you amplify the energy, but how you put the energy in the larger spatial scales. Make sense? So that's the separation I am making. Starting with turbulence, are you going to be generating large-scale structures? If you're looking at the sun, these are the small-scale structures, full desk magnetogram from the Solar Dynamics Observatory, and you can go into smaller and smaller scales. And here is a movie, though, put together by David Hathaway, of small-scale fields coexisting with large-scale ones, and you actually begin to see how it goes through, vanishes, and then reappears again. And this is all observations. These movies are all made out of observations running from 1980 to 2005 data. So you're looking at, it looks like a computer simulation, but it isn't. It's just raw data coming out that is put together in a movie where you begin to see large-scale patterns superimposed on small scales, a disappearance of the magnetic fields altogether, the so-called solar minimum, and the reappearance. So any theory of the dynamo which tries to make sense of this must explain, first, the generation of large scales from small scales, and two, this 11-year cycle. This has not happened except phenomenologically. Theorists think that they can go ahead and put parameters in equations and they can fit this somehow. And that sort of exercise has happened in the community. And Eugene Parker always has a good joke, and he says, you want me to fit anything in life? Just give me 3 parameters and I can fit the Manhattan skyline, right? So with 3 parameters in life, you can fit anything. So this magnetic field can also be explained by 4 or 5 parameters. That's not physics. That's parameter fitting. What you would be successful in saying that you have a model, that parameter fitting can be useful because it might allow you to sort of crystallize what does the turbulence have to do in order to generate that structure. But the question will remain. So suppose if you start with MHD models and you can actually generate this, that would be more first principles, and that is in fact the unsolved problem. And people like mathematicians have in fact said, what would it take for us to really have a dynamo theory? So suppose if you have a magnetic loop, and let's start from a very, very simple system. You take a magnetic loop, like a rubber band, if you will, stretch it, twist it, okay? And you could either have magnetic reconnection occurring at this level, breaking it off, and you get a larger loop, or you could fold over it, and there'll be tremendous tension building up in these corners, snip it off, and you can actually get magnetic field loops coming out of that. And you can go through this repacking procedure. So the combination of turbulent stretching and twisting and folding, you can come up with scenarios where you can get magnetic field amplification. The kinematic dynamo problem became the privy of a lot of mathematicians and is discussed extensively in the monograph of Steve Childress at the Courant Institute of Mathematical Sciences and Andrew Sword. There's a monograph on kinematic dynamo theory that you might want to look at. It's full of wonderful mappings. They've taken that problem and converted it into a 2-dimensional map, and they brought in the techniques of nonlinear dynamics to bear on that problem. And what they're asking is the following. Give me a velocity field. Can I solve the induction equation? and get an eigenvalue for growth of the B magnetic field that is as weakly dependent on dissipation, namely Rm, as you can. That's the kinematic dynamo problem. And the answer that came out of that work is, yes, nature has a dynamo. That in fact, given a certain velocity fields, you can be certainly inventive about the velocity fields so you can get magnetic field amplification and you can make it weakly dependent on the magnetic Reynolds number. And people went into this in some depth. How weak can you make it? Is it a log Rm or a log log Rm or a log 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 Rm, and on it goes. Very sophisticated mathematics, but solving a simple equation and trying to see how we can make the magnetic field growth as weakly dependent on Rm as possible. Now, what does reconnection play a role in? Plays a role in essentially simplifying the topology, because imagine if you didn't have reconnection, what would happen? You take this rubber tube, you twist it, you fold it, you twist it again, fold it. Can you imagine the tension that builds up at the joints? How far can you twist this rubber tube if the rubber tube doesn't break? Try it with a newspaper. You'll run out of steam with a few sheets of paper. That unless you break the newspaper, you can't really continue folding and twisting, right? So that's what reconnection comes in at a very subtle level. Without reconnection, Alfvén's theorem would take magnetic fields, swing it around in its topology, absolutely contort itself the hell out, look totally weird and not go anywhere, and after a while the process is going to saturate itself because there's no relief of the tension that is building up. What reconnection does is to come and simplify that process. Where the tension, the current density is built up a lot, comes and says, let me reconnect and relieve the tension. That's what happened at that corner when you got those two things out of there. So reconnection therefore allowed you to simplify the topology, as we were discussing in the previous lecture. So in some sense, fast reconnection must occur in dynamo theory. And if it doesn't occur fast enough, then dynamo theory can't go anywhere. Because Alfvén's theorem would just get yourself tied in horrible knots that you won't know how to get large-scale structure out of, okay? So what happened in this mathematical literature is that influence of magnetic diffusivity on growth rate became the dominant thing. People were after fast dynamos, where the growth rate becomes independent of Rm, the stretch, twist, fold mechanism, or the slow dynamo, growth rate limited by resistivity, the scenario that I was talking about. Fast dynamo is relevant for most astrophysical objects since Rm is much greater than 1, and dynamos including reconnection steps can be fast provided the reconnection is fast. Looking at kinematic dynamo theory, going back to say the 1980s, you would think problem is solved. We can't really find these dynamos. Once again, computer simulations got in our way. And I'm going to get to that in a moment, but I want to just mention to you certain things about the sun's magnetic field before I get into a discussion of what the problems of kinematic dynamo theory was. At the level of kinematic dynamo theory, the answer is that you give me a large-scale velocity field, and if I give you the freedom to choose that, there were many velocity fields that you could come up with for which the induction equation does show you large-scale amplification that is weakly dependent on the magnetic Reynolds number. Okay. However, what kind of dimensionality do you need to operate in? Can you do that in 2D? Can you do that in 3D? And these are the questions that got a lot of attention from people, and I want to just illustrate that in the context of the sun. In the sun, as I was telling you, there is a radiative zone, and then some part of it, about 30% of it, say, is where you have a convection dominated. And what helioseismology did was gave us measurements of the type of magnetic fields and convection patterns that can be sustained below the surface. Our knowledge of the sun is skin deep, but it is extremely important knowledge because it tells us what is going on in the convection zone and how that is different from what goes on in the radiative zone. One of the really striking discoveries of helioseismology was that there is a sharp layer at which the radial convection patterns that you see in the radiative zone become very different in nature. It's called the convection zone, the solar convection zone. The magnetic field is written in terms of a component in the phi direction, a two-dimensional component that can be written in terms of the stream function A, The velocity has three components. This is in fact the rotation of the sun, and differential rotation is the most dominant shear flow in stellar convection zones. So if you take this form of the equations and you plug it into your induction equation, you will get a set of two coupled equations, one for the toroidal component and the other for the poloidal component. The meridional flow is the independent advection of poloidal and toroidal field. So this, if you look at these patterns, these are the blue terms, the green terms. I want to explain the significance of all of them. Let me just say that the diffusion terms are ones that are indicated in red. They're there in both equations. Now, the differential rotation is the source for the toroidal field. And let me explain what I mean by that. Let's go back to the previous slide. The toroidal field is this B. So the question that you ask yourself is, if you should start out with an A, can you produce a B? Okay? The answer is, yes, you can. If you start out with an A, you can produce a B through coupling with these terms. So if you have a poloidal flow, because if this poloidal flow were not there, this equation would have no way of actually coupling to this equation. So the poloidal flow allows you to do that. Diffusion is a sink for poloidal and toroidal field. No term is capable of maintaining the poloidal field against ohmic decay. Look at this equation. This equation affects this equation, but B does not enter this equation at all. So if you left this equation purely by itself, you're not going to get a reinforcement of the poloidal field from this equation. And therefore, you need actually something else that's happening. And what kind of motions would allow you to produce such a field? Cowling proved a theorem many, many years ago, which is called the anti-Dynamo theorem. And his essential point was that if you have a stationary axisymmetric magnetic fields with currents limited to a finite volume in space, that you cannot maintain this by a velocity field with finite amplitude. In other words, if you have an ignorable coordinate in the system, axisymmetry means you have an ignorable coordinate in the system, you cannot have maintenance of that magnetic field. So anything that sustains this magnetic field will have to break the axisymmetry. So that tells you then, already gives you a hint that if you rely only two-dimensional turbulence, these equations are nonlinear, so you make a study of two-dimensional turbulence of these situations. You can get all kinds of interesting behavior, but what you will not get out of it is a mechanism that will find a way to sustain this magnetic field against diffusion. So that gives you a powerful hint of what kind of magnetic fields, what kind of velocity fields we really need to have. Now, what people are after, if you think about it, is to try to figure out a robust mechanism that will allow them to generate large-scale magnetic fields given that you have small-scale turbulence. How do we understand that? Steenbeck, Krauss, and Radler posed the problem in a mathematical way. What they said was, take the induction equation that you know and you've seen and average it. Okay? So just as you were saying, write V as V bar plus V prime, which is a fluctuating term, and you average that equation, you get an equation for the mean B field. So everything is mean here, except this term, which is a beating of two terms, V prime cross B prime. Remember, the total equation is linear, but I've broken the total. Are you guys with me? Am I going too fast? You'll stop me. Okay. So I've taken the B term, and I've now broken it into two terms. A mean term B, which has an overbar on it, and a fluctuation, which has a prime quantity on it. Then I average the whole equation. And every term in the equation is linear except the V cross B term, which is a product of two terms, V bar cross B and V prime cross B prime. There are other terms, which is V prime average cross B bar, which drops out, or B prime average cross V bar, which drops out because fluctuating terms by themselves, when you average them, go to zero. It's when you beat them is when they stay. This term is called the turbulent EMF in dynamo theory. E bar is written at V prime cross B prime. And so look at this term now. You took an equation for total B and you generated now a term which depends on the nature of the fluctuations in the system. This is an exact equation. Take this equation and subtract it from the total equation, B. Then you can generate an equation for the fluctuation B prime. And that's what this one looks like. These are both exact equations. Are you with me? Right? Notice that this equation, you come to this term and now you have this sort of a behavior, V prime cross B prime minus average of V prime cross B prime in the fluctuation equation. To solve this equation, you really would need an equation for V prime cross B prime. So you go to the MHD equations and you say, I want to solve the, let me write the time-dependent equation for V prime cross B prime. You know what's going to happen to you? What's going to happen? What will that equation have? It will have terms which are products of three perturbed quantities. It's called the hierarchy problem that happens in every equation like this on Earth. Every time you want to solve the problem, you're pushed to a higher order. You'll be left with terms which, the equation for V prime cross B prime will have terms like V prime cross B prime cross V prime, averaged. Then you have to write an equation for the 3-point term and the 4-point term, and on you go. And it's not a hierarchy that truncates. Useless. Formally correct, but useless. So what the kinematic dynamo theory people did is to come out and say, I'm just going to drop these two terms. It's a huge uncontrolled approximation, but I'm going to drop it. The advantage would be, then, if I want to solve this equation, this is exact, all I need to do is to solve for this guy, and I can solve for this guy. And how will I solve for this guy? Well, V prime I'm going to prescribe. B prime I'm going to solve by solving this equation. This guy is not going to get in my way. For prescribed V prime, I'm going to solve this equation, plug it in, and I'm going to solve those two equations because they're closed and proceed forward to tell you what the mean magnetic field is. Well, that's what Steenbeck, Krauss, and Radler actually tried to do. So I'm sorry, it'll look a little formal and don't have to understand everything. But in general, they were mathematicians and they were going at this problem. Okay, so that approximation of neglecting those two terms, that was fine. Then they go ahead and said, well, let me try therefore to solve for this turbulent EMF term. They wrote this out in terms of integrals, did some scale separations, and what basically they came to was this, that the turbulent EMF could be written as a combination of two terms, approximately. One was proportional to the mean B field, and the other which is proportional to some sort of a current density. Okay? Don't let me confuse you with too many indices here. Basically, at the end of the day, I'm going to get to the answer without trying to take it step by step. This is what kinematic dynamo theory essentially gave you. What it gave you was an overall turbulent EMF multiplying alpha, the mean B field B, another term which is convection-like gamma cross B, a term that looks almost dissipative, beta curl cross B, so on and so forth. The turbulent EMF in this exercise is being written now in terms of the mean B fields. The advantage therefore is, if you, after all this algebra, if you go back to the mean B field equation, imagine now you actually know what this term is. That goes like alpha B, beta J, all mean field quantities. So you say, I have the effect of turbulence effectively included through my alpha effect or beta effect. I can solve the mean B equation, and then I have the time evolution equation for B. Great. They said, what do I need to have in order for amplification of the magnetic field? What they said was, that if the turbulence has some nice properties, you can actually show, in fact, a lot of mathematics went into it, but they essentially argued that if the turbulence is isotropic and if it doesn't have mirror symmetry, then you will have a non-vanishing alpha, which will essentially enable you to get amplification of the magnetic field, despite the fact that the turbulence can produce dissipation that will tend to decay the magnetic field. So the net physics output of kinematic dynamo theory was that it said, if you give me non-mirror symmetric turbulence, I can amplify the mean B field by a certain amount, and you will see growth in the magnetic field. So except for the restriction of non-mirror symmetric fields, and so you could come up with a whole bunch of turbulent velocity fields that have these symmetry properties, you would get amplification. In particular, they showed that alpha depends on V dot, and this is fluctuation of the velocity field, this is the vorticity field, omega dot V is the term. So if you have omega dot V 0, then alpha will be 0. Now look at turbulence that is 2D. If V lies only in a plane, and curl V would lie perpendicular to the plane, V dot omega would be 0. So alpha would be 0 for a purely 2D velocity field. This is consistent with Cowling. Cowling said if you have a symmetry direction whereby you essentially have a two-dimensionalization of the velocity field, you can never amplify. Here, it turns out that kinematic dynamo theory gave a satisfying answer. It said if you don't have this non-mirror symmetric thing, which requires essentially 3D motions, you're going to not get amplification. All that you will get is enhanced dissipation. V squared you can always get in 2D. That's not going to give rise to any amplified magnetic fields. People never felt that they had gotten around the objection of Cowling, that you can't do things in an axisymmetric domain. You have to go to 3D. In 3D, the turbulence must be non-symmetric. You'll get a finite alpha. You're in business. So the dynamo problem then essentially became the alpha problem. And it turns out that if you had alpha effect, that problem of the solar dynamo problem becomes essentially now solvable, because now you have an additional term, alpha B, that couples the poloidal and the toroidal field. As long as alpha is non-zero, you postulate some alpha from this, you can solve these two equations and they'll keep each other up to turbulent regeneration, overcoming the effect of dissipation. To this day, if you go to HAO in Boulder, you have a whole lot of people doing what they call flux transport dynamo problems, where they posit that you give them alpha. In fact, they have complicated functionals for alpha that can make sense of the sun's convection pattern. And very good work and in the sense of trying to make sense of the Earth's magnetic field. What that does not answer very well, and you'll see why, is that is this alpha real? We forget sometimes that the alpha came from a highly simplified theory. And what was this highly simplified theory? It threw out the complexity of MHD altogether. It said, let me just solve the kinematic problem. And the kinematic problem was, let me start out with the induction equation, prescribe a velocity field, that'll amplify the magnetic field, and that's the story. But what happens in life, in MHD simulations, is that as the magnetic field grows, other equations that you neglected, such as the momentum equation, comes into play. The velocity that you prescribe will then be affected by the magnetic field that velocity grows, which is called the effect of self-consistency or feedback. The question is now, imagine you posited that you got this alpha effect out of the induction equation. And then if I asked you the question, well, will this alpha effect survive in a completely realistic MHD flow where you have a lot of equations coming back? And this led to, I was going to show you here, don't worry, the solar convection zone, these alpha effects do work and produce it. But the non-kinematic ways is proper way to treat them is 3D simulation. Still very challenging. Has been successful for geodynamo, but not for solar dynamo. And what is happening is that as the magnetic field grows, the Lorentz force term in the momentum equation of MHT, remember J cross P minus grad P, that's growing. What is that going to do? That's going to change the V through the momentum equation. The question now arises, you start out with a kinematic dynamo, the magnetic field grows, and before it grows to saturation, the momentum equation acts back on this magnetic field. And what if it now acts to defeat the alpha effect? You have to demonstrate that alpha does not quench, that alpha does not die when we take into account the effect of the back reaction. Do you guys understand this problem, why kinematic is not sufficient? Because we have to go back. I really don't want you to lose the big picture here. Forget the algebra things. That don't matter very much. What I'm talking about here is that you can solve this equation in isolation. And that's what kinematic dynamo theory did. So the magnetic field is now growing. Okay? In the beginning, this J cross B term is very weak. So whatever velocity field you had, fine, at least for a while, without the magnetic field acting back on it. But now the B grows, the J grows, J cross B is acting on this. That's going to change the V that you started out with. And what if it changed in a way that suppressed your alpha effect? Well, guess what? You ask a question, you hope the news is not bad, and the news is bad. What happens is that people found, at least this came out of the Chicago group's work, Fausto Catania, Robert Rosner, and others, and they seem to find too much alpha. Quenching is happening, things were saturating too rapidly. So I want to now go to what's going on here is that there was a very nice paper by Pouquet et al. Back in 1976, which actually people didn't fully appreciate the significance of until these pessimistic results started coming about. And Pouquet, trying to solve the turbulence problem, realized that the alpha effect is actually modified, this omega dot V that you saw me talk about, by a Lorentz force correction, J prime dot B prime, which had sign different than the omega prime dot V prime term, which was driving the alpha effect in the first place. And if you thought that turbulence tended to give you alphenic solutions of the kind that V is proportional to B, then the curl of V gives you omega and the curl of B gives you J. This suggested that there will be near perfect cancellation as J and B grows of the alpha effect, and things are going to die. And this is what came to be known as the alpha quenching mechanism. Now, before that, it's not like people were stupid about it. People knew that nonlinearity was going to become important. But they assumed that the quenching was a lot less drastic than it actually was. So this happened, and there were a lot of people who actually tried to also question this. What are the challenges? Let me summarize it. Smaller scales, in fact, Russell Culstrode and Anderson did a very nice calculation. They say, you start out with a low-level mean field and a fluctuation. You know what happens? The very beginning, the fluctuations that grow very, very rapidly, while the mean hasn't grown very much. It, in fact, grows to equipotation so rapidly, yeah, the small-scale dynamo problem is solved, but you haven't gotten a lot of mean growth. Due to constraints of magnetic helicity conservation, small-scale fields act back to decrease the large-scale field growth drastically. The problem of catastrophic quenching, Gruzinov and Diamond, Catania and Hughes. But this challenge could be addressed, and some creative people like Blackman and Field and others said, you know what's happening? If you insist that you're going to get no transport of magnetic helicity, you're going to live with this problem. What really happens in systems that are astrophysical, you have open fluxes of magnetic helicity coming in that is going to allow you to get around this problem of alpha quenching. And those arguments have weight. But now we are going outside of the scope of our treatment. This classical dynamo theory was done as a closed box, nothing coming in, and alpha quenching was there. And Blackman and Field are telling you, well, we can get around this problem by maybe injecting helicity from the outside, and may be a way around it. But be that as it may, at even moderate Rm, the fast-growing small-scale dynamo implies that velocity fluctuations should always be accompanied by magnetic fluctuations of a similar magnitude. And this is where I was referring to Shekouchihin's paper. He actually showed that this is going to happen, questioning the relevance of classical dynamo theory. What Shekouchihin and others essentially said was, well, you're going to get small-scale dynamo, and that's fine. And they solve for the spectra. They have a lot of numerical simulation. I would say that problem is quite believably understood in that you do get small-scale dynamo. Even if that magnetic field energy was very, very small in the beginning, the fluctuations can grow, not large-scale flux. If you take the average over a certain domain, the positive delta B and the negative delta B will cancel out and will not give you much mean field growth, but you'll get energy. So that problem is solved, but the problem remained regarding how to get around this problem. What am I doing with time, Sasha? Am I okay? 2:30 I stop, right? No, what am I saying? 15 minutes I stop, right? I think it's a fair statement that this issue remains open in terms of how do we get large-scale magnetic fields from turbulent fluctuations. The good news is that we have some rigorous results. We have Karlik's theorem. Anti-dynamo theorem doesn't help you, but at least tells you what you need to have. And we are along the right paths by thinking about what generic properties of turbulent fluctuations we need in order to get mean magnetic field growth. And people are investigating these mechanisms, and that's fine. But the large-scale dynamo problem does not have a robust solution yet. What I'm going to talk to you about is a possible solution in a context of the accretion disk that my former student Jonathan Squire worked on. And he actually got the Marshall Rosenbluth Dissertation Prize on this about 2 years ago. He's had a very good early career, but I want to talk to him about his thesis to you because it actually has conceptually certain ideas that are potentially, I think, very important. What John Esquire actually did was to look at the problem of the accretion disk and the magnetic field. Now, we do not have direct measurements of magnetic fields near accretion disk, but we have some wonderful simulations. And a persistent feature of these simulations is, and they're mostly MHD simulations, is that when you run them with high resolution, you find that, first of all, there's a magnetorotational instability, which goes unstable. And the magnetorotational instability was discovered by Chandrasekhar and Velikov many, many years ago. But they didn't fully, Chandrasekhar, as usual, did a superb job of the stability analysis, and it's there in his book. But he didn't really explore the consequences of it for angular momentum transport. It was Steve Bulbus and John Hawley who talked about the MRI having potentially important significance for angular momentum transport in accretion disks. So what they found was a very striking instability. You could call it the Chandrasekhar-Velikov Bulbus-Hawley instability, long sequences of names, where hydrodynamically a disk with Keplerian flow is actually stable. But if you put in a little bit of magnetic field in it, it excites a very interesting instability for which the growth rate does not depend on the strength of the magnetic field, but the magnetic field's presence actually enables the instability to be excited. Otherwise, if you just do hydrodynamic stability theory, you're not going to get any instability out of it. For Keplerian flows, you can actually show the thing is pretty stable. So the use of the MRI, and they were looking at momentum transport. That has led to a whole industry of papers. They got the Shaw Award in recent years, and people have essentially studied the magnetorotational instability problem. And what do you see in these simulations? What you see is that you get large-scale magnetic field growth in these systems. And the mechanism of why that occurs, I'm not talking direct observations. I'm talking simulations. I wish observations were there to vindicate these simulations, but we probably won't. It's not easy to get those things, as you know. But at least we have the simulations which tell us that these simulations have large-scale dynamo in them. It'll be good to do a theory for it. Now, if you look at the whole thing with kinematic dynamo theory and the corrections of alpha quenching and all of that, where were we? We were in the situation where we said, well, you start out with an instability. What it's going to do is to produce a tremendous level of low-level fluctuations, which are going to quickly rise to equipartition. They're not going to amplify the mean magnetic field much, because alpha quenching is going to kill you, unless you're saved by boundary conditions bringing in helicity and so on and so forth. But let's, for the moment, not worry about these sources, because these simulations don't have these sources in them. But they saw amplification anyway. So what John Esquire did was essentially to look at this problem. And this is from Jacob Simons. He's an active person in this field. He's also from Boulder. Is he still in Boulder, Leah?
He got a faculty job for next year
at Iowa State. So he's moving to Iowa State. I should congratulate Jake. Okay. He is now going to where I was for many years at the University of Iowa. It would have been nice if he were there when I was there, so we could have worked together. But anyway, so he's moving. So Jake Simon actually has very nice pictures in his website, which I recommend you. But he's integrating the full compressible MHD equations. These resolutions are very useful, but these simulations are very useful, but they're not sufficiently well resolved to really nail the dynamo problem. And so you need to go to more special models to get that. And one way to study the accretion disk problem is to take this little thing and blow it up. And you can do the compressible local MHD equations, which is called the stratified shearing box. And then we can go to a further limit, which is unstratified, that is no density gradients and things like that, and study this problem. And this is the problem that John Esquire actually studied using the incompressible MHD equations. And so the simplest relevant system exhibiting MRI turbulence is the local incompressible MHD equations, remove global curvature, blow up this box with appropriate boundary conditions, which are a proxy for what's going to happen in the global simulation. Boundary conditions are periodic in Y. So this is the theta direction. So this theta direction is periodic, right? So you impose in the shearing box periodicity conditions in theta, because Y is like theta, and Z, and shearing periodic in X. So special boundary conditions. It's called shearing box, and you run these simulations. Don't worry about the details of all of this. And what John Esquire said was that we're going to study this mean field flow setup in MRI, a simple model, and ask whether you can produce mean magnetic fields arising out of the MRI turbulence in an unstratified system, and try to understand what this is about. And the bottom line of his work is that he actually found a new dynamo mechanism. And it's not just another term in the equation. It does amount to that, but it's actually something that is quite surprising. And this is the part that excited me the most, is that, see, the way in which dynamo theory was going was, we had this alpha quenching problem, right? You started out with some fluctuations, you put in a velocity field. In this particular case, the accretion disk's large-scale flow. What it'll do is that it'll produce magnetic fluctuations. And what was dynamo theory preparing us for? The small-scale dynamo is going to overpower any mean field growth. So small-scale dynamo, in short, was bad. It was bad for mean field growth because it rises so rapidly, the fluctuations grow so much more rapidly compared with mean field growth, and they act back through the quenching mechanism and don't allow the mean field growth to go. What Squire said was, no, allow the small-scale magnetic fields to grow to saturation, and you will find that in the post-saturation phase of the small-scale dynamo, driven by the magnetic noise, the mean field will grow. So the small-scale dynamo then, through a forcing mechanism in a late time scale, an essentially nonlinear mechanism, will end up driving your means field growth. And he wrote 8 papers on the subject, all of it, none of which by itself conclusively nails it, but if you do all these other calculations, he arrived at the same conclusion. I'll take your question now and I'll go back to his. Yeah.
Yes, sir. For MRI, you need to start MRI, you need initially a small magnetic field.
Correct.
So at some certain level of the field, the MRI will no longer.
Correct. So he had that seed magnetic field to grow too.
Right. So what if the dynamo mechanism grows the magnetic field? Will it stop MRI at some point?
So
Or do you just initially need a small magnetic field?
you initially need a small magnetic field. In all these problems, even in the kinematic dynamo problem, as you know, as I was saying, it's a linear equation in B. So think of it as an eigenvalue problem where you write B as del going like some B0 times e to the power sigma t, where sigma is the exponent you want to compute. Without a B0, you don't go anywhere anyway in this problem. So you have to start with a seed field, but you start with a very, very small field and you amplify it. So is it true for all of this stuff. But what is happening is that in most cases, when you start with the seed field, the fluctuations grow so much more rapidly than the mean field that they completely overwhelm any mean field growth. So people said your small scale growth just about completely overwhelms your mean field growth, and you don't get much mean flux at all. Small scale dynamo is therefore terrible for mean field growth. So quenching, it kills you. Squire's conclusion was, in the context of the MRI, that you actually follow through with the small scale fluctuations where the mean is going at a lower rate. Small scale will saturate and then drive means field. The latter is what he said was facilitated by the magnetic shear current effect, an essentially nonlinear effect. So let me proceed now. And what he did was that he actually analytically demonstrated it in 2 papers where Rm much smaller than 1, where perturbation theory is very good. That's not the relevant regime for accretion disk, because you really want to be in the much larger Rm. But if you're trying to prove a point of principle, you want to check. Suppose if you do the low Rm problem where you can do perturbation theory, are you going to get a result that is inconsistent with what you're... He showed analytically, in fact, that this is happening. But it's not applicable to the accretion disk, so he did a bunch of other things. So let me summarize his result for you. Small-scale magnetic fields have a positive effect on the large-scale dynamo. The effect requires velocity shear, so Keplerian. And in fact, he was doing this problem without an alpha effect. He deliberately chose the flow to be such that V dot omega was actually, that alpha, the kinematic alpha, is actually 0. So you ask, you've been telling me all along that you need E equals alpha B minus beta J. You've said alpha equals 0 and beta is going to have you completely dissipate. How are you getting growth? Jono argued that beta is actually a tensor, that it has off-diagonal elements, and if they have negative sign, then they will actually drive magnetic field growth. So this was a novel kind of dynamo because it is not the alpha dynamo. It's actually a beta dynamo, but a sort of negative resistivity, if you will, which of course diagonal terms, due to physical reasons, you can rule out that cannot be the case. But non-diagonal elements, off-diagonal, can actually have the right sign to give you amplification. So he argued we should care about this. Why? Magnetic shear current effect seems a likely candidate for the central unstratified dynamo. More generally, this is what he was driving at. This is why I was excited about his thesis on ST-Lam. He sort of put dynamo theory on its head. He said, saturated state of small-scale dynamo, which was regarded as deleterious for mean field growth, actually in the saturated state drives a large-scale dynamo. Almost like inverse quenching could be applicable to the sun and sun-like stars. Even though whether the MRI applies to the sun or sun-like stars, we do not know. And in fact, I have a graduate student now, Valentin Skutnev, who is actually working with Keaton and Lequanet and others to actually try to look at whether the magnetic shear current effect can actually work in the sun or not. And the instability is vastly different, and we have to redo everything. But the notion that you can, in fact, drive an off-diagonal element of a turbulent resistivity to have growth happening if it has the right sign was, in fact, the major conceptual advance made. He ran Snoopy, and, uh, and that too at moderate resolution to make this point, is that you see here energy growth. So the fast growth of small-scale dynamo, this is a small-scale dynamo. There you get energy growth, okay? No mean flux. It saturates, okay? And then you get, now, when you look at the magnetic field plots, he ran a lot of runs. You begin to see large-scale growth appearing well after this has happened. And when you look at the spectra, you actually find that due to the presence of rotation, that's why he's doing two cases, omega equals 0 and Keplerian, he was able to show analytically that in some limits, this is coming out of the perturbation theory. And I'm just ending on this note because I don't think we have a lot of time to talk about the details of this. He did, in fact, get simulation and analytic results to agree where analytic theory was applicable. He ran simulations in that domain as well. And good evidence that the magnetic shear current effect is responsible for unstratified MRI dynamo. If you look at the work of Shi, Stone, and Huang, they actually have a section on this. We are revisiting this carefully again now. But the preliminary indicators are that the dynamo that they see in the unstratified case, they actually computed this so-called negative resistivity by test field methods. Stone and others did that, and their results seem to be consistent. A lot more to be done. Shear flows being ubiquitous, is the magnetic shear current effect important for the sun? I leave this as an unsolved problem, but what I was very interested in was this science paper published by Hotta, Rempel, and Yokoyama. They actually didn't know about our shear current effect at all. What they were doing is the following. They ran two simulations, one in which they didn't resolve the small scales very well, deliberately. And then they found that the solar dynamo goes through alpha quenching, very similar to the kind that you've already heard me talk about. And then they refined their simulation to capture the small scale fluctuations as well. They found mean magnetic field growth. Their point was, and this was a numerical point, that if you want to study the dynamo problem, that makes the dynamo problem so much harder in astrophysical objects, that if you really want a resolution of this problem, where you have convection playing a very important role, if you actually don't resolve the small scales, you will get the wrong results on the growth of the large scale fields. So unless you go from the small to the large, you don't get a dynamo in the problem. They, of course, did not identify the shear current effect or anything like that as a scale, but the simulation is very impressive and suggests that you need to resolve both scales. What Jana would say is, tentatively, that if the shear current effect, and that's a big if, is operating in the sun, then it may be playing a role somewhat similar to what it does in the accretion disk. Namely that the small scale fields go more rapidly, they saturate faster, and then that forces the large scale fields to grow a subsequent era of growth that could bring the magnetic fields up to the observed magnitude in the simulations. No final word on this. That's the end of the story. Thank you very much for your attention.
So
I'm
what
sorry?
did you find for the magneticity in the shear current?
For the what?
For the magneticity.
Oh, you know what? We didn't study it enough. This needs to be understood. The work that the French group have done leaves it inconclusive as to whether helicity is playing an important role in that. In other words, is looking at helicity conservation a way of trying to understand the magnetic shear current effect. I think we need to explore this.
Yes, because if you grow any helical large scale fields, you grow small scale helicity, which would be the alpha m, which could quench in the
I think it's plausible. Need to study it. I know Eric has done a lot of work. You doing work on this area too. It'd be really nice to connect up the simulations and analysis, and it's not been done yet. It's not a question that was settled in Squire's thesis.
If small scale taken field, the turbulence is giving rise to large scale fields, then can we interpret it as maybe an inverse transfer inverse cascade of
Sure,
velocity of
sure. This is the, yeah, exactly. So there are no theorems where you can actually track it and see whether you are getting a similar thing. You know, studies have been done by Lazur using Snoopy code, and he has written a couple of papers on this. If you look at his papers, the evidence is not compelling that this inverse cascade he's been able to establish using his result. I think we need to look at this again. I'd like to understand the connection between helicity and the magnetic shear current effect. Either there is one or there is none. I'd like to know what it is. It's plausible what you say, but we haven't proven it. These simulations, we saw no plasmoids. And I think that our resolution is not high enough to catch the instability of thin current sheets in this sort of a thing. Some of the other changing the magnetic Reynolds number at the level that we have, that where you can actually believe our results, don't seem to have a tremendously important effect. So the shear current effect does not rely much on the instability, the plasmoid instability of thin current sheets. You get thin current sheets in the system, but there's so much sheared flow. I mean, this is something that, you know, I've talked with Jim about, and Jim says that when he makes a real effort to study current sheets, what he finds is that there's certainly plasmoid instabilities occur, but he has a lot going on. He has also a lot of sheared flows, and these plasmoids are torn apart at times. And I can totally believe it, because I've put focus on that in studying the instability of these thin current sheets. But in an accretion disk, you have a lot going on. But on the other hand, if you look at Chuan-Fei Dong's work, which I showed near the end of my last talk, you saw that if you ran it at a Lundquist number of, a magnetic Reynolds number of a few thousand, he didn't see any plasmoid instabilities either. He had to go to a substantially higher this, whereupon he saw them, and he saw that the spectrum was being modified. I think we need to study this more with more resolution before we can resolve it one way or the other, and I haven't made up my mind on this. Leah.
So how is the magnetic shear current effect different from other effects that depend on rotation, like the omega cross J effect?
Those effects are there. They are related as well. So yeah, the omega cross J, does that produce a negative anomalous resistivity? What we've been able to do is to show that the shear current effect produces a negative off diagonal beta. And this comes out of the analysis. And it's independent of the system size to the extent that we can analyze it, no such term. And so that differentiates from the stochastic alpha effect. But these things may be present simultaneously, and in a code to separate them out, I think requires careful study. Any other? There was, other than Leah, I saw another hand go up. Okay. If not, it's been a pleasure. I have had much more fun than you've had, I'm sure. It's a lot easier to be here than sitting down there and listening to somebody speaking for 3 hours. Thank you for your attention, and have a great summer school.